Well, hello, Seven Blue. Happy Tuesday. Hope you're doing well. Sorry, there's probably movement sounds. There you go. Okay, we're going to double lesson. And the reason why is because these two lessons are relatively related to each other, and I think we can do them. So first we're going to focus on the ratio of side lengths of right triangles. And we've talked about right triangles quite a bit. Right triangles move us into a realm of math called trigonometry. And what trigonometry is basically the study of the relationships between the angles and sides of triangles. And it usually starts with a study of right triangles. I'm going to draw 3 right triangles that I want you to draw as well. And we're going to talk about these relationships. Now, if I focus on this angle, then I can identify certain sides. And I can name this side, well, that side is clearly the hypotenuse. And the hypotenuse of a triangle will never change. However, these other 2 sides I'm going to talk about, depending on which angle I'm focused on, will change. This side, because in relationship to the blue angle, I'd have to call that the opposite side. And that's going to be very important as we move forward. This side would be called the adjacent side, because that's all in relationship to the blue angle. It's the side next to the blue angle. The red thing, the opposite, is opposite the blue angle. And again, the hypotenuse would never change. If I go over to this middle triangle and I focus on that blue angle, then clearly this is my hypotenuse. Again, that will never change. The hypotenuse is always opposite the right angle. This side would become my opposite, and this side would be my adjacent. Opposite, it's across from the blue angle. Adjacent, it's next to. If I then focused on this angle, clearly my hypotenuse wouldn't change, because hypotenuse is always where it is. However, what would I call these 2 sides? Is it my opposite? Is my adjacent? And that's why we don't really focus on the right angle when dealing with trig. We focus on the non-right angles and determine our opposites and adjacents from that. Let's move forward, because this is a kind of a question mark. Okay. We are going to talk about this triangle. I know you recognize it's a 3, 4, 5. And we're going to talk about the ratio of side lengths. Sorry, that's misspelled. I can't really change it now, or that would mess up everything. So we're going to look at the ratio of side lengths, and we're going to talk about angle A. So we're focused on angle A. And then we're going to say, hey, what's the ratio of the opposite to the hypotenuse? And we want to focus on the opposite would be this right here, that side length that is 3. So I'll put a 3. And we're creating ratios, so I'll put a fraction bar. To the hypotenuse, well, we know the hypotenuse is this 5, so that would be 3 to 5. And what we often do is turn these into decimal form, and we should know that 3 to 5 is equal to 0.6 or 6/10. All right, let's do some more. Let's go from our adjacent to our hypotenuse. So again, focused on angle A, the adjacent would have to be this one, right? That would be the side length of 4. And so I will put that down as a 4. My hypotenuse has not changed. It's still the 5, so we'll say that. And in decimal form, we would say that's 0.8 or 8/10. All right, last one we got to do. So we're going to do our opposite to our adjacent. So again, the opposite hasn't changed. It's still the 3. And the adjacent, well, that hasn't changed either, so it's still the 4. And so we would say the decimal form of this is clearly 75 hundredths or 0.75. Now this opens us up into trig, and I'm going to kind of name these. We will do a trig lesson a little bit later on. But right now, this first ratio we looked at is called sine, S-I-N-E. And we would say that the sine of angle A is equal to 3 to 5 or 0.6. This next one is called cosine, C-O-S-I-N-E, angle A. The cosine of angle A is equal to 4 to 5 or 0.8. And then the last one is called tangent, T-A-N-G-E-N-T. The tangent of angle A is 3 to 4 or 0.75. All right, let's try this one more time, focusing on those same kind of ratios. Let's look at this one. Go ahead and draw it up. I've got triangle RST. I've identified side length RS as 2, ST as 1. We're going to focus on angle R, and I want to first work on my opposite to adjacent, or maybe that's all I'll do. So here's the thing. I know that my opposite for angle R would be this side length. So I'll put a 1. Now, again, I'm creating a ratio, so there's my fraction bar. But here's the issue. What's my adjacent? What is this side length? Well, so clearly in that this is a right triangle, you could use the Pythagorean theorem, or maybe if I draw it this way, it'll help you a little bit. And instead of calling it 1, I'm going to call it x. And instead of that 2, I'll say 2x. Now, that is something you should recognize as a special right triangle. And in this, I want you to have that memorized, that this would be x rad 3. Therefore, the length of the brown side, RT, is rad 3. So I can say rad 3. Now, to turn this into a decimal, we're only going to be able to go approximate. What you would do is you would take your calculator, you'd have to landscape orientation it, hit 1, hit divided by, hit 3, and then hit the square root symbol, and then press the equal sign. And usually we'll find that these, because they go on forever, why? Well, it's an irrational number, we'll just go to the thousandths place. So rounded to the thousandths place, if you did that with your calculator, you'd end up at 0.577. Now, if you're like, really? Wait, I didn't do it. Maybe pause and go grab a calculator and check it out, because what you would do is, again, landscape orientation it, hit 1, hit divided by, hit 3, and then hit that square root symbol, but then you have to hit equals after that. And you should end up with something that rounds to 0.577. Let's press on to the secondary idea. I want you to draw a triangle that looks like this. I'm sorry, I have all this information. I forgot to pull it back. Here it is. Okay, so go ahead and draw up a triangle ABC. And what we're going to do is we're going to focus on the angle with the least degrees. And hopefully looking at this, you'd have to say, well, angle A is definitely the smallest angle. And that's true. So I can say that the measure of angle A would be less than, notice how those things look very different, but the way I draw them, I can tell between the two. You should too. Some of you had trouble with that. When you do an angle sign, it looks like a less than sign. Try and work on that, because this looks clear to me. So what would be the next angle if we were going from least to greatest? Clearly, it would be angle B. It's still an acute angle. So I'll say the measure of angle A is less than the measure of angle B. And then after that, what would be the next greatest? Well, there's only one more. So it would definitely be the measure of angle C, which is our only obtuse angle. Now, if I focus on the sides that are opposite those angles, so the side opposite angle A would be angle BC. I'm sorry, side BC. And that would have to be, just by looking at it, you'd be like, well, that's the least one, right? So then, if I focus on angle B, the side opposite is side AC, and that would be the next greatest side. So I'll say AC. Then, clearly, we only have one side left, and it would be the one that's opposite angle C, and that would be side AB, which is our longest. And this is an important truth about angles and triangles and side lengths, that the angles are related to their opposite sides. So if I look at angle A, I know its opposite side is BC, and they are very related to one another. Now, you might also think about the converse of this, that sides are related to their opposite angles. So if I consider something like side BC, I know that that's related to its opposite angle, which is side angle A. And it's related in this kind of greater to lesser or lesser to greater sort of way. So if we saw something like this, and they draw it up, and we want to know the side lengths from least to greatest, we'd first have to think about, okay, well, they give us two angles. What's angle P equal to? Well, I do know that the sum of the angles in the triangle is 180. So I can take this 59 and 61 and add that up at 120. And clearly 180 minus 120 is 60 degrees. So now, focused on the least angle, which is angle R, I know its opposite side is side PQ. Therefore, that must be the smallest side, or the least side, if you will. What's next? Okay, so we have angle P that comes in at 60 degrees. Its opposite side is side QR. And then clearly the greatest side must be the one opposite the greatest angle, which would be the greatest angle is angle Q at 61 degrees, therefore side PR. So that's one way of thinking about it. The other way would be doing just the opposite. What if we wanted to name our angles from least to greatest? Well, we know it's related to its opposite side, so we see that the smallest side is this side 7, which is related to its opposite angle, which is angle C. Therefore, angle C must be the smallest. I go on. So we see that side BC, this 8, is the next in line, if you will, or the next greatest. And its opposite angle is angle A. So therefore, angle A must be the next greatest. And then clearly, we focus on the greatest side length of 9. We determine its opposite angle, angle B. Therefore, angle B must be the greatest. Kind of a simple idea, maybe one you've considered before. Hey, last problem. Write it all down. They give us some good information. We have triangle ABC, 2 angles are named, 1 side length is named. We have triangle WXY, 2 angles are named, 1 side length is named. They give us further information that side AC is equal to 6 centimeters. And the question is why? No, just kidding. It's not why. They want to know what the side length of WY is. So, okay, first let's focus on this first triangle here. We notice that it has 40 degrees and 85 degrees. So to determine what angle A is, we'd say 180, that's the whole, minus 40 plus 85 is 125. And we go, okay, so that one's 55 degrees. Well, then when we look at the second triangle, we'll see, well, we've got a 55 and an 85. Well, we know that it must be 40 because that's what the rest of the numbers would give us. Therefore, we see that the angle measurements are congruent. Corresponding angle measurements are congruent. So we can make a similar statement and say that triangle ABC is similar to triangle WYX. Or, I'm sorry, WXY. That does matter. Because what I want to do is make some corresponding sort of statements. So notice how I can connect my they also tell us that AC is 6 centimeters. I'm just going to write that in right now. So if I think about WY, that's WY. Well, notice how that connects to my AC. And so I can say AC is proportional to WY, or they're corresponding. Now I can also focus on that they tell me that AB is 8 centimeters. And so AB will be the same or will be corresponding to WX. And I have those two side lengths. So I'll go AB at 8, WX at 6, and then I'm going to focus on this blue AC to WY. Well, they tell me that AC is 6 centimeters, and WY is the thing I don't know. And then I form my proportion. Ready? 1, 2, 3. All right. So 8x is equal to 36. Divide both sides by 8. I'll go, so that would be 8 goes into 36 4 times with 4 left over, 4 of 8. So that's the same as 4.5. But remember, this is centimeters, so I'd say 4.5 centimeters. Yeah? Kind of a cool idea. I hope you enjoyed it. So we're not doing the split. I'm just going to ask you to do the real deal Holyfield homework of homework 112. Don't worry about how that affects things once we hit 115. I've got it all mapped out for you, but I'm glad we had a double lesson. I hope you're doing well. You can reach out to me anytime. HW112. Take good care. Bye.